Hi. Today I'm presenting my work done during my master's thesis at Nile University. And this work was joint with Mustafa Yusuf and Onu Rozan and Hisham ElGamal from Ohio State. So the title is Randomization for Secrecy in Two-Way Channels. We'll first start with introduction of secure communication and why is it needed. So I guess fundamentally it's needed because not everybody is on the good team, is in the good team. So we have to deal with this. And this picture shows that usually security will come at a price. So secure communication, there are many applications to secure communications. Integrity, where you want to make sure that the received message has not been altered by a non-legitimate entity. Authentication, which is clear from the name. Non-repudiation, like signature, where you want to make sure that the transmitter cannot refute about the received message. So the problem of interest is confidentiality, where two users want to communicate in the presence of an eavesdropper and want to keep this communication secure from the eavesdropper. So we'll talk about the information theoretic approach and how can it be useful for practical applications. The problem of interest is confidential digital communication over the wireless channel. Classical approaches like computationally secure systems, for example public key cryptography, which assumes a limited computational power at the non-legitimate entity, or what we call the eavesdropper, by having mathematical functions that are hard to inverse. So this is fundamentally different from the information theoretic approach, where we use the notion of perfect secrecy defined by Claude Shannon in 1949, which says that the a priori and a posteriori distribution of the message given the observation at the eavesdropper should be the same if you want to achieve perfect secrecy. So the first paper by Claude Shannon was kind of pessimistic, that it showed that this is possible only if under the condition that a secret key with an entropy at least equal to the entropy of the message is available. So an alternative approach to this, so Shannon's paper relied on an assumption of noiseless communication. So if we want to go to more realistic settings, like the more faithful models to the wireless channel, we can see that we can exploit features specific to this medium to achieve secrecy. And that only not offer fundamental results where we want to understand the limits or the maximum achievable rates, but also low complexity approaches where we don't require the nodes to do heavily computational operations. So features specific to the wireless medium are broadcast, interference, and fading, and we want to see how those can be good or bad for our purpose. So our work at the Wireless Network Center in Nile University had those 4 lines of work, where the first one used the fading property, and the second one, secrecy in Wi-Fi networks, that shows the practical approach of how information theory can be useful for practical applications, where in this work we dealt with the Wi-Fi network as a de facto and try to develop protocols based on information theoretic insights that can enhance the current implemented protocols for the Wi-Fi network. And what I'm going to talk about today is the two-way secrecy in two-way channels, where we have two nodes want to communicate messages, want to interchange messages to each other in the presence of an eavesdropper. The basic assumption is that the practical application which we can think of is when both users want to communicate in the presence of an eavesdropper that cannot lie inside a circle centered halfway between the two nodes. So as we will see, that kind of model will be an ideal candidate for our solution. So the model is that we have two-way communication. We have two scenarios assuming full and half duplex antennas at both nodes, and communication takes place in the presence of a single passive eavesdropper, and passive is an important assumption. And we will look at the discrete memoryless channels modulo 2 and Gaussian channels. So the performance metric, we define a rate as achievable. We say that the rate is achievable if for any given epsilon we can achieve the reliability and secrecy constraints with this negligible probability of error or probability or leakage of information to the eavesdropper. So instead of perfect secrecy, we now have this weaker secrecy condition, which can make our problem more tractable. The state of the art in this problem is to extend current approaches available for the one-way channel with feedback. Feedback means that the legitimate receiver can transmit something to confuse the eavesdropper. And this was introduced first by Maury through the public discussion channel, which is a noiseless channel available to everyone, but the trick is the eavesdropper is passive while the legitimate receiver is active. So we'll see exactly how this works, but we used this to achieve secrecy. And then this was extended to a more realistic setting where feedback can actually be transmitted over the same noisy channel as the forward channel. And also we have results for the two-way channel that are only concerned with maximizing the sum rate using two approaches, random binning and cooperative jamming. This will be defined later. So consider the one-way channel under the full duplex scenario. To see how feedback can be useful, consider a simple example of a modulo 2 channel with error-free transmission. Then the full duplex receiver can transmit a symbol XF, which takes 1 or 0 with equal probability. Then that's XORed with the forward channel symbol will create an ambiguity at the eavesdropper such that the entropy of the original message will be equal to 1, which is the maximum, which is the same as the entropy of the message before the observation. So that's simple. The receiver randomizes a signal, and that signal confuses the eavesdropper. And the trick here is that the receiver can transmit, but the eavesdropper cannot transmit. So in this way, the receiver can create an advantage over the eavesdropper. So we can, that's in one-way channels. The simple extension to this in two-way channels is to have a TDMA scheme, where in the first time slot, receiver user 2 is receiving, and in the second time slot, user 1 is receiving. So going to the two-way channel, the key idea, so we can think of this as creating a prefix or an artificial channel before our original channel that takes place before our original channel, a randomization. And this randomization can happen at both nodes simultaneously. It doesn't have to be TDMA. So this will be clear very soon right now. So we call this idea channel prefixing, where we add a prefix channel that inserts artificial noise in the channel to confuse the eavesdropper. And the other idea is random binning, and that's an idea that was originally introduced by Weiner in the 70s. When nature is already generous to you, so there is an advantage which you can use. You can have a structured randomness to exploit this advantage to achieve perfect secrecy or secrecy advantage over the eavesdropper. The other two ideas will apply in the half-duplex scenarios, as we will see. Randomized scheduling, where the two nodes randomize their transmission schedule, and randomized power allocation. So the key idea is to insert a prefix channel to alter channel conditions in favor of legitimate nodes, and then use random binning to create this, to exploit the secrecy advantage to achieve perfect secrecy. The problem with classical approaches using only random binning is sometimes you don't have this secrecy advantage. That's when channel prefixing can be useful. And joint optimization is allowed of binning codebooks and prefix channel distributions. So channel prefixing in a discrete mirrorless channel is just adding a channel, our symbols, the encoded symbols for our message is C1 and C2, and we add a prefix channel before the transmit symbols X1 and X2. In a modulo 2 channel, this will correspond to XORing and a new variable N1 dash or N2 dash at user 1 and user 2 respectively, where we control the error probability, or the probability that N1 dash equals 1 and the probability that N2 dash equals 1. In the Gaussian model, we split our power, our transmit power, between rho 1C, which is used for transmitting C, and rho 1N, which is used for just inserting a Gaussian noise. And random binning is when you already have a secrecy, when your channel gives you a secrecy advantage, which means that the mutual information between the transmit symbol and the received, the transmit random variable X and the received random variable Y is greater than the mutual information between X and Z, where Z is the observation at the eavesdropper. So in this case, we add a redundancy in our message, in a sense that we create more code words than we need, and each set or each bin of those code words represent the same message. So the code word is randomly selected within the bin. So the message determines the bin index, while the code word is randomly selected within the bin. If our randomization rate is such that is equal to the mutual information between the transmitted message from both users and the eavesdropper, then the ambiguity at the eavesdropper will be a cloud whose size is equal to the cardinality of the alphabet of the desired message. One more tool we will need is private key sharing, which allows one user to transfer its available secrecy rate to the other user. So user 1 can physically secure the transmission. Instead of transmitting its code word, it will transmit a private key to user 2, which uses it in the next block. So that if user 2 doesn't have, if nature was not generous enough to user 2 but was to user 1, then user 1 can transfer some of its available rate to user 2. So it doesn't increase the sum rate, because the rate we gain, the secrecy rate we gain for user 2 will be lost from user 1, but it allows us for distributing the rate between the two users. So it gives us one more degree of freedom in distributing the rate. And that makes the individual rates, the individual rate constraints will be only the reliable communication conditions or the main channel capacities in absence of the secrecy constraint. So here the individual rate constraints will be only the main channel capacities. So the secrecy constraint appear only in the sum rate. So numerical results, here we can show that user 2 has a good channel and user 1 has a bad channel. That's for the modulo 2 case. In that simple model, we can see that in order to achieve the maximum at user 2, user 1 would better jam than transmit. So channel prefixing only, which is the green line, achieves the maximum we can have. So user 1's rate would rather be 0 if user 2 want to achieve its maximum. On the other hand, if user 1 want to achieve its maximum, user 2 would rather transmit than jam the channel. So because user 2 has a good channel. So in that case, random binning achieves the maximum we have, the corner point. However, that's not the case in the Gaussian channel. So I'll skip this and go for the half duplex. So to see how this can be useful for the half duplex, we return back to our simple example where the receiver can randomize a transmit signal and jams the channel with this signal. However, here the receiver will have to face a trade-off between receiving and sending the feedback. So using this simple scheme, RS, the secure rate can be maximum half, where the receiver will listen half the time and transmit the other half. But the trick is the eavesdropper do not know the symbols at which the receiver is receiving or transmitting or jamming the channel. So in a half duplex channel, we have the randomized scheduling idea where both users are randomizing their transmit schedule. So any given time interval can be either Alice is active, Bob is active, concurrent transmission, or silence. In our analysis, in order to highlight the advantage given by randomized scheduling, we give the state 2 and 3 to both to everybody, including the eavesdropper. So I'll go fast on this. Yeah, here in the analysis, to simplify the analysis, we don't consider randomized transmit power, but there is a possibility that the eavesdropper can identify the source of transmission by its received power signal. So we assume that the received power at the eavesdropper is the same from both transmitters. However, this might not be practical, so in a practical scenario, we need to randomize the transmit power. So how much time?
2 minutes.
2 minutes, okay. So we consider a more practical scenario where we apply the randomized transmit power idea, and we also assume some other realistic assumptions, like instead of Gaussian input distribution, we have BPSK encoding. For simplicity, we have a free space path loss model and hard decision decoding at everybody, and we assume energy-based detection at the eavesdropper. We have an implementation of a test bed for our experimental results, which was a nice experience where we have seen some of the practical challenges to applying these ideas. Like, for example, we have to apply the randomized scheduling idea, we have to remove the SYSMA CA protocol from the radio stack of both transmitters. So because of the PPSK assumption, now we have a binary symmetric channel, which is evident from the rates. We can go to the numerical and experimental results. Here, Dmin over Dmax shows the ratio between the distance between Alice to Eve and from Bob to Eve. So as this ratio goes to 1, it means that Eve is of equal distance to both Alice and Bob, and that will give us the maximum secrecy rate we can get. And on the other hand, as this distance goes to 0, means that the eavesdropper is very close to one transmitter than the other, which gives a 0 secrecy rate. In summary, the information theoretic paradigm offers provable security in a sense that we can guarantee security even in the presence of a passive eavesdropper which have unlimited computational power. Structural insights like randomized, like the ideas of randomized scheduling and putting that in more general frameworks, abstract frameworks like channel prefixing can help build up on this work. exploiting the wireless medium can also be useful to achieve low complexity secure protocols. And last, revisiting the assumptions even to more realistic settings, like going from the one-way communication to two-way communication, or from Gaussian input distribution to BPSK encoding, or from Maury's public discussion noiseless channel to feedback over the same noisy channel, can even make the problem more tractable or easier to solve. This work was presented in GlobeCom, ITW, and hopefully will be submitted soon to IEEE transactions. Thanks.